Okay. Here it is. Hello. Okay, I think it's time to start. So, any question from this time? Otherwise, let's finish teleportation, and we will talk about new subject about density matrix later. Okay. So, but let's first finish teleportation. So this is a protocol that shows us how a composite quantum system works. But yeah, so let's start from the setup of teleportation first. So teleportation, we have two body alias Bob, and they met a very long time ago, and they share the EPR pair. And now the question is, alias want to send Bob unknown quantum state by sending only classical message. Okay. And this is really only a hard problem because unknown quantum state is very weird. So if Alice want to send information about any classical state to Bob, then she can just copy the classical string and send that to Bob. But as we said before, it is very hard to know what the unknown quantum state is. In particular, that's because when you measure it, it just collapses into something, and then you lose information about this unknown quantum state. Okay, so in quantum teleportation, we want to send the unknown quantum state to our other party. Well, one way is you just hold whatever physical copy that's holding this unknown quantum state and send it to Bob. But that requires sending a quantum state. You need some way to send quantum information. If you can only send classical information, then we need this quantum teleportation protocol. Okay. And yeah, so the quantum teleportation protocol, we have Alice and Bob share EPR pair, and Alice have another unknown quantum state, and she wants Bob to hold this unknown quantum state. She wants Bob to have exactly this unknown quantum state. Okay, at the end of the protocol. And so the protocol, well, the protocol has several steps. And as he described, the first step is Alice is holding two qubits, and Bob is holding one qubit. So Alice is going to so we start with this unknown quantum state. We just have it arbitrarily parameterized by A0 plus B1. So the starting state is this psi, which is A0 plus B1, and beta 00. Okay. And so beta 00 once again is this EPR pair, so means 00 plus 11 over square root 2. Okay? And so the first qubit is on Alice side, so this 00 is on Alice, and this 01, this 10, this 11 is on Alice side, and this 1, this 0, and the 1, and 0, and 1 are on Bob's side. Okay, so we start with this state, and then first thing Alice do is something new we talk about now. Okay, so it's a 2 qubit gate. This gate depends on one qubit and acts on another qubit. So it's a control NOT gate. So it says it reads the first qubit in computational basis. If it's 0, then it does nothing. And if the first qubit is 1, then flip the second qubit. So that's why we start from 0 plus 1 here, and turn into 1 0 and 0 1, because the first qubit is 1 here, so then the second qubit got flipped from 0 to 1, and the second qubit here got flipped from 1 to 0. Okay, so this is the control NOT gate. It's a very classical gate because it basically acts on computational basis. It says basically says read your state in computational basis and see where the first qubit is 1. If it's 1, then flip the second qubit. Okay, the CNOT gate is same as the classical CNOT gate, except that it can act on superposition of state. Okay. So in classical circuit, we also have CNOT gate that will say you read the first bit and flip the second bit depending on whether the first bit is 0 or 1. Okay, control NOT. And now the quantum circuit, we can, so here is an example saying that we can apply any classical gate on quantum circuit. Okay, although we haven't really talked about quantum circuit. Okay, and in quantum circuit, you can also apply any classical gate on quantum circuit. Just you need to read your the input state as a superposition of this computational basis state, and you do whatever classical thing you need to do on your computational basis states. Okay, so that's the control NOT gate. For now, easiest way to define it on quantum circuit is thinking about defining it on these 2 qubit states. 2 qubit space. So 2 qubit is a 4-dimensional space, so we just have a 4x4 matrix here. And it says if your first qubit is 0, then we do identity. We do nothing to the second qubit, and the first qubit is 1, then we do this NOT gate. So we flip the second qubit. Okay, and as we know, and here we use our rule for composite system. So we say CNOT gate only acts on the first qubit, but our system actually has 3 qubits. Okay, and so what happened is, so how do we write down this CNOT gate on 3 qubits? Is it means that it's identity on the third qubit. So the gate we do on those 3 qubit states are CNOT tensor identity on third qubit. And so in theory, you can write down this gate. So this will be an 8x8 gate, and you think you can write down a huge 8x8 gate matrix here and multiply by this 8-dimensional vector. But it's not really recommended. Later we'll talk about this in most formal way. But in particular, although everything is defined as an 8x8 matrix and 8-dimensional vector, etc. here, but it's really not recommended to do calculation that way, just because writing down an 8x8 matrix takes you a lot of time. Okay, here, so you can see that here we do things in a smarter way. So we think CNOT is, well, when it acts on computational basis, it has this specific rule where you read the first qubit and see what it do on the second qubit, and you see that we can just by eyeball see what CNOT do on our input state. So you just read the first qubit and see where the second qubit got flipped. Okay, so that's the CNOT gate. And then next we do Hadamard gate on the first qubit. And once again, Hadamard gate is 1 over square root 2, 1, 1, 1 minus 1 gate. And in particular, Hadamard gate will flip between the eigenvectors of the z operator, so the computational basis is 0 and 1, and the eigenvectors of the x operator, poly x operator, so this is plus and minus. And so those are identity we talked about in the first week. So Hadamard on the Kate 0 state is a Kate plus state, and Hadamard on Kate 1 state is a Kate 0 state. So and by our composite rule, similar to the previous one, if we do Hadamard on the first qubit, so then is a Hadamard on first qubit. We tensor identity on second and third qubit. This is actually the gate we apply on those 3 qubits. Okay, and this is a tensor product structure. So once again, when we apply it on this, it's easier to just apply on tensor product states. Then you just do each qubit each tensor slot 1 by 1. So identity on the other things, identity doesn't change anything, and so we just apply Hadamard on the first qubit. So Hadamard on first qubit, then this 0 will change to plus, and this 1 will change to minus. So this is exactly what we get. So the second and third qubit stay the same because they are acted on by identity. And the Hadamard on first qubit give you 0 plus 1 here and 0 minus 1 here. Okay, and also extra 1 over square root 2, so you get 1 over 2 here instead of 1 over square root 2 here. Okay, so Hadamard on first qubit, and we reorder things. So because we know the next step we are going to measure on the first 2 qubits. So we group together, so we sort those things by what are on the first qubit. So first qubit can have 4 possibilities. It can be 0, 0, 0, 1, 1, 0, and 1, 1. So we group them together. So in particular, that's a peak one of them. So maybe 1, 0 turn. So we see which turns we have 1, 0. So we have 1, 0 here, 1, 0, 0. And so this 0 has coefficient a and 1 over 2. So everything has coefficient 1 over 2, 1 over 2 on the outside. And this 1, 0, 0 has coefficient a, so we can put this coefficient a with this 0. Because tensor products, you can put the scalars on every for tensor product, we know scalar multiplying on each part is the same because they are a product. And so this is 1, 0, 0 with coefficient a. And also we have 1, 0, 1 here with coefficient minus b here. Okay, so it's a0 minus b, and you can check that we have those 4 calculations correct. Okay, so 0, 0 with a0 plus b1, and so here we see the nice thing. So this a0 plus b1, this is the input state side. Okay, and then we have a similar thing, but not quite the same. So you see everything has a and b here, but with slight difference. So here we have a1 plus b0, here we have a0 minus b1, and here we have a1 minus b0. Okay, and I believe this is what we talked about last time, about when we finish. And the next step we have is we measure in computational basis. Okay, and once again, measurement in computational basis. It's easier to think about this in the generalized measurement formulation. Okay, so what we do is we project states on 4 different projectors, right? So measure in computational basis is you apply the projector onto the computational basis on your state. So you have the projector 0, 0 is a projector on 0, which is 0, 0 ket, and 0, 0 bra, or this is 0, 1 ket, 0, 1 bra, and so let's write down the 4 projectors, and then we have 1, 0 ket, 1, 0 bra, and 1, 1 ket, and 1, 1 bra. Okay, so those are the okay, now it's ugly. Okay, so that's not right here because we have dot dot dot. Okay, and yeah, so we have a projector onto those 4 states. The measurement operator you apply on the first 2 qubit, and once again, as a rule of composite system, so when you have a measurement operator on part of your system, then the measurement operator on the whole system is you just tensor identity on other part of your system. So in particular, measure operator on 0, 0 was this projector on 0, 0 on the first 2 qubit, and then this measurement operator on the whole 3 qubit system is just this 0, 0 projector tensor this identity matrix on third one. Okay, similarly you have the 0, 1 projector tensor identity on the third one. Okay, so you have those 8-dimensional projectors, and you can act on your state. And but it's pretty easy to see what happens for when you do those projector on the state here, because we already written in good form. Okay, so in particular, if we apply or for example, if you apply this 0, 0 tensor I3 projector onto our states here, then you see that the projector acts on this 0, 0, A0 plus B1 state, then the 0, 0 part stays 0, 0. Okay, and but if you have a projector on all other 3 states, then it will be 0, 0. Then the inner product will be 0, just because the computational bases are also going to each other. So let's write down one of the pretty trivial computation here. So for example, we have 0, 0 projector tensor identity 3 acting on this maybe we don't need to write 3 here. Okay, so 0, 0 projector tensor identity and act on our 0, 1 A1 plus B0 Then by our tensor product rule, then each slot should act separately because we have the first two qubit things tensor the third qubit, and here we have the first two qubit thing tensor the third qubit, so they should act separately. So this should equal to this 0, projector act on 0, 1, and tensor product identity acting on A1 plus B0. And then this is 0, so this is really put everything 0. So this is scalar 0 times 0, 0, and tensor product identity acting on this thing doesn't change anything. A1 plus B0. Okay, but well, everything is multiplied by this 0, so this is just 0. Okay, so this has no amplitude. Okay, and so you can similarly see that 0, 0 acts on 0, 1 give you 0. And 0, 0 act or sorry, 0, 0 inter product with 0, 1 give you 0, then 0, 0 inter product with 1, 0 or 1, 1 are all going to give you 0. Okay, so 0, 0 acting on all those three terms will give you 0, so you are only left with the first one. Okay, so the first one you are left with the post measurement state is 0, 0 tensor A0 plus B1, and you can check this is normalized. Okay. And then this is normalized, and the probability of getting this outcome is proportional to amplitude squared. Amplitude is 1 over 2, and amplitude is 1 over 2. So so the probability is 1 over 4. Okay. So when you the outcome you measure outcome 0, 0. The post measurement state is 0, 0 tensor A0 plus B1 with probability 1 over 4. And similarly, when you measure 0, 1, then all those three, so this 0, 0 term, 1, 0 term, and 1, 1 term is 0 inner product or 0 projection onto your 0, 1, 0, 1 ket 0, 1 bra projector. Okay, okay, and so when you try to get the outcome 0, 1, then this 0, 0, 1, 0, and 1, 1 states has 0 amplitude on your projector, and you are left with this 0, 1 tensor A1 plus B0 state. Okay, so that's why you have 0, 1 tensor A1 plus B0 here. And once again, you can see this state is already normalized because 0, 1 is already normalized, and we know A squared plus B squared equal to 1. Okay. And so the amplitude here is 1 over 2, and once again, the probability is 1 over 4. And so similarly, you get this 1, 0 state with 1, 0 tensor A0 minus B1. So 1, 0 tensor A0 minus B1, and you get 1, 1 state with A1 minus B0. 1, 1 tensor A1 minus B0. Okay. So this is what happens when it is a major state. Then Alice will know which of the four outcomes she gets, because we know when we do measurement, we know the outcome. So Alice will know whether she measures 0 or 0, 1 or 1, 0 or 1, 1. And so now here is some weird quantum thing happen. So we think the after the measurement is done, then bubble state changes instantaneously. Okay. So remember the first qubit on Alice side, and the third qubit is on Bob side. Okay, so this is something weirder than you might think. So still this is on Alice side, and this is on Bob side. Okay, and so something interesting happens. So depending on what's Alice's measurement outcome, Bob will have different stage he holds, and this really changes instantaneously. Okay. And so Bob used to have this weird entangled state, but after measurement outcome, so you see that the Edison state and the Bob state is actually not entangled. So they will have one of the four product state between Alice side and Bob side, and so they have one of the four state, which is some part on Alice and some state on Alice side, tensor with some state on Bob side. Okay, so really measurement can break entanglement. You measure on one side, and and you will have you might break the entanglement between this side and this side. Okay, and yeah, and here we see that so if they are very lucky, say Alice measure the 0, outcome, and as we say, this A0 plus B1 state is exactly the state we want to send to Bob. Okay, so if Alice measures 0, outcome, then we're already done. So 1/4 probability the protocol just succeeded. Okay, so Bob will hold this. But unfortunately, there are 3 possible outcomes, and so we know each of the 4 each of the 4 outcomes happen with equal probability, and so we need to do something else when Alice got the 3 other outcomes. Okay, and that's exactly why Alice needs to send the result to Bob. Okay, so Alice needs to say, hey, I actually measure 0, or 0, 1, or 1, 0, or 1, 1. Okay. And Bob will know, okay, so if Alice measures 0, then I need to do nothing, okay? If Alice measures 0, then Bob know they are already done. Bob already know hold the original state that Alice want to send, okay? But now the question is, if Alice measure other thing, then Bob get these 3 different states. And fortunately, those states, although they are not quite A0 to B1, they still have this A1, AB structure, so Bob can do something that doesn't depend on A and B to correct it back to the A0 plus B1. Okay, so remember the result we want is psi equal to A0 plus B1. Okay, and yeah, those 3 states, they are not A0 plus B1, but they are pretty close. And in particular, so say if you get this A1 plus B0, okay, if you get this A1 plus B0, you can just apply a X gate on it. So you apply a X gate on it, then 1 changes to 0 and the 0 changes to 1, so you just get A0 plus B1. And similarly, if you have A0 minus B1 and you apply Z gate on it, then Z on 0 is still 0 and the Z on 1 give you minus sign before your 1, so the minus sign will cancel this minus sign and once again give you A0 plus B1. Okay, and yeah, and you can check it yourself. You apply X gate first on this and then Z gate, then you will also get back to A0 plus B1. Okay, so although Bob get one of the 4 random states, if Alice told him that which one of the 4 states Bob get, Bob can always correct the state back to A0 to plus B1, and that complete the teleportation protocol. So we know that whatever one of the 4 measurement outcome Alice get, Bob can always correct his state and get A0 plus B1 on his side. Okay. And we have a more mathematical way to write those 4 things we do here. We say that if we if we have the measurement outcome N1 and N2, then Bob will apply Z to the N1 and X to the N2. Okay. This is really just summarizing those 4 things we do here. Okay. And here is more summarization. That is, we can write everything in quantum circuit. And so here is a small example of a quantum circuit before we actually have the quantum circuit. Okay. I think it is okay. So the quantum circuit is what happened in this protocol. So we have a 3 qubit. So Alice and Bob, so those 2 qubits are held by Alice and this qubit is held by Bob. Okay. And so we know Alice and Bob start with 3 qubits, where the second qubit and the 3rd qubit is in this beta 00 EPR pair state. And Alice has an unknown quantum state site here. And what Alice do is she do a C-NOT gate, so she control on first qubit and apply a NOT gate on the second qubit. Then she apply a Hadamard gate. Then she measure her qubits in computational basis, both qubits in computational basis, and in particular, same as measure each one in its computational basis. Okay, so computational basis of 2 qubit is the tensor product of computational basis on each qubit. This is pretty trivial. Yeah. And then based on then we say that Alice need to send the measurement result to Bob, and Bob will apply some correction. So if the second qubit is M2, then Bob need to do X to the M2. X to the N2 means that if M2 is 0, then don't do X, and if M2 is 1, then apply X gate. Okay. and also do z to n1 means that if the measurement result is 0, don't do anything here. If the measurement result is 1, do a z-get here. And as our explicit calculation shows, Bob will always get this side which is equal to a0 plus b1. So this is equal to a0 plus b1, and the outcome will be a0 plus b1. Okay, and yeah, so that's the protocol, and I want to finish this by giving some high-level points on quantum teleportation. Okay, and so first thing is something that makes the physicists think very weird. Think the protocol is kind of weird. So this is this is what I guess famously Einstein finds quantum mechanics very weird. That is, you found out that when Alice and Bob's state are entangled, Bob's state change immediately after Alice's measurement. So this is called I think this is a word coined by Einstein called spooky action at distance. Okay. So this makes physics really unhappy because, especially for Einstein, because Einstein says that information can only travel at the speed of light. Okay, right? So Einstein says that the information can only travel at the speed of light. Then how can your quantum measurement change some state immediately at some place very far away? You remember that when we have this Alice and Bob model, we didn't say anything about their distance. So Alice and Bob can be really far away. Maybe Alice is on Earth and Bob is on Mars. Okay, and yeah, but in terms of quantum mechanics here, we think that the states are changing immediately. Okay, so how does this not break Einstein's relativity, where this Bob state change at faster than speed of light? That is, this spring action at distance actually don't contain any information, because before Alice and the measurement come to Bob, Bob has one of the four states here, and so we think Bob has one of the four states here, but if Bob doesn't know which measurement count it is, even though he holds one of the four states, actually you can prove that Bob yeah, so just by the density matrix formulation we'll see very soon, you can see that if Bob has 1/4 probability to hold those four states, he actually has no information about A0 plus B1. He cannot learn anything about A and B by holding equal mixture of those four states. Okay? So even though we think Bob's state changes immediately because he has this probability mixture here, Bob actually don't go and gain any information about that. Okay? So yeah, so there is no faster than speed of light communication. Okay. Yeah. So no faster than light. Okay. Okay. So yeah, quantum mechanics is this collapse of quantum state is really weird action. You think something really changed, but it doesn't contain any information. Okay. And yeah. And so something even weirder is that, okay, you think, so this Bob state here doesn't contain any information about A and B, doesn't contain any information about your side. And then maybe the information is your measurement outcome M1 and 2, okay? But it's pretty easy to see that M1 and 2 also contain no information about side, because as we just showed here, M1 and 2 is drawn with probability, uniform probability 1/4. This probability 1/4 doesn't depend on your A and B at all. Okay, so and 1 and 2 also contain no information about your state. Okay, so you see there's something very funny happen here. So right after you do measurement here, kind of like no one has information about psi. So we know this part doesn't. If you only have this part, you don't know psi, and but you only know M1 and 2, you also don't know about psi. So really, you need to combine this M1 and 2 and whatever state Bobs hold here. So only when you combine the information, you can correct back. You can do this correction back and get your psi. Okay. So only when you both know the measurement outcome and you have those post-measurement state, or maybe this slide is better. Only when you both know this one and this one, you can know psi. Okay. So psi is kind of living in this weird correlation between the measurement outcome and the post-measurement state here. Okay. It's really interesting. Okay. So yeah, M1 and 2 doesn't know anything about psi, and bubble state, residual state doesn't know anything about psi, but the correlation kind of know. Okay. And so when you combine M1 and 2 and the bubble state, after measurement, you can recover your psi. That's teleportation. Okay. And also there is one more principle we don't want to break. That is that is we don't want no cloning. Okay. And you can easily see that at least after completion of the teleportation protocol, at least part is destroyed by the measurement collapsing. Okay, like you see here. So really, at least here the post measurement state is random 1 and 2, random computational basis and 1 and 2. So after we do the measurement, it is only holding this random 0, 0, 0, 1, 1, 0, 1, 1. So at least also don't hold information about psi anymore. Psi is totally on pub side, and this is consistent with our our previous statement that saying that there is no cloning in quantum information because psi was an unknown quantum state, and Alice and Bob didn't actually try to know psi. They tried only to try to move it around. So at least part of psi is going to totally destroy it. The psi is perfectly appeared in Bob's side. Okay. And yeah, so that's quantum teleportation. Any more questions? Okay. Later, think a little about look at the teleportation circuit and think a little bit about the weirdness of quantum information. We send this unknown quantum state from Alice side to Bob's side. And no one really learns about psi in the middle part, but somehow it transformed perfectly from Alice side to Bob's side. Okay, and if we're okay with quantum teleportation, then we'll switch gear and switch slide to let's see, it's a little tricky. Now switch gear and switch slide to this density operator one. Let's see if our streaming still work. Not quite. Let's see. Oh, okay. Here we are. Okay, and yeah, and yeah. So we are going to talk about density operator or density matrix. I guess teleportation serves as a good way to motivate our density operator. Okay, so remember in our in the middle part of the teleportation protocol, we said that Bob is going to hold a really weird state. So Bob is going to hold with 1/4 probability each one of them, and the state A0 plus B1. Or A1 plus B0, or A0 minus B1, or the latest one, I think is A1 minus B0. Yeah. But anyway, Bob is going to hold this weird state. Okay. So yeah, so we can write this the situation Bob is in this weird way. So Bob is we say Bob hold 1/4 state with 1/4 probability. Okay. And kind of what we want to do in density operator is we try to give this more a cleaner formulation. So what does it mean for Bob to hold 1/4 state? Can we write this weird expression in one clean quantity? So I think that's the motivation here. And really here, I want to make a distinction here. Distinction here is something very weird here is there is a difference between superposition and the classical probability mixture. Okay, and so for example, in this state here, in this pure state here, A0 plus B1, we think it as a superposition between the 0 state and the 1 state with coefficient is complex coefficient A and B. Okay, so there is really a difference between, but But then before those two states, between those four states, we are doing a classical probability mixture. We are not doing quantum superposition. Okay. So this is really something I want to make a distinction here. I guess yeah. So superposition and classical probability are different things, and yeah. And in particular, I guess you can see homework or example we'll do later. Yeah, we are not really doing a superposition of those four things, okay? Because yeah, if those four things together, that's not not the same thing as you will get from the classical probability mixture of those four states. Okay. And anyway, so that's what we want to do now. We are going to describe this probability mixture of states, of quantum states. They are actually going to become matrix, which we call density operator or density matrix. And yeah, as we said, it considers the classical probability mixture of quantum state. And really, these quantum states are quantum superposition of different basis elements, and it's different from classical probability mixture. Okay. And yeah, so we start with this part of kind of derivation of the density matrix. Okay. Okay. So we have a probability mixture of states. Okay. So we write it in very abstract way. So we have some states psi. Okay. Psi, and they are indexed by this I. So we have a set of states psi I, and each state happens with classical probability pi. So for example, here we have P1 1 over 4 equal to this state A0 plus B1, and P2 1 over 4 equal to this state A1 plus B0, etc. Okay, so you have probabilities associated with states. Okay, and so we want to know how should we describe this system, and then maybe in particular want to say what happens when we measure this system, because remember, when we say we want to get information or classical information out of a quantum system, you need to do a measurement. Classical, you need to do a quantum measurement, right? Okay, so in particular, we measure some operator A, so some physical operator A, and so we say what is the expectation value of A when you are given some state psi I, some set of state psi I with probability pi. Okay. And then that should be, well, expectation value is linear in probability. So you know each psi I give you expectation value is just you sandwich A between psi I. So okay, so each psi I has expectation value this psi I A psi I, and then you have probability over different I, then you just average according to your probability. This makes a lot of sense. This is the expectation value. So you have different parts with different expectation value, then each part has its probability, then just do more averaging. So summation pi over the expectation value of each psi on A. Okay, and then now we do something weird. Okay, yeah. So we say okay, so this is a number, and a number can be viewed as a 1 by 1 matrix, so we can say this number is a trace of itself, because trace of a 1 by 1 matrix is the same as itself. And then we use the seeking property of trace. Okay, and I guess if you want to do a lot of more steps, then it's more tricky because you have pi here. Let me see. Yeah. But also pi is trace is linear in pi, so we can kind of put pi anywhere. Okay. And also this is matrix multiplication here, so you can just put pi everywhere. But the important part here is the seeking property of trace. Okay. So if you look at those three things, okay. So this is a row vector, matrix, and a column vector. Okay. So this part, I guess on this part, and so this kind of a symmetry A between side, you can also view it as a matrix multiplication. So this is like an n by 1 matrix, n by n matrix, and n by, oh sorry, 1 by n. Okay, 1 by n by n, and n by 1 matrix. Okay, so you view those three terms as a matrix multiplication, then you can use the seeking property of trace to move these two terms to front. So you have A psi here. Okay. So you use put the sticky property to move this A psi to front. Okay. And you know trace is the same because trace is a cyclic property. The cyclic property that trace AB equal to trace BA for any matrix. Okay. Trace is a cyclic property. And then PI. Okay, so PI should be here, but really matrix multiplication you can put PI anywhere. So I'll put PI here. Okay, and yeah, okay, and then you have this both the trace and the matrix multiplication is linear. So you can also put the summation I inside. Okay, okay, and yeah. So if we also move the summation I inside, then we really have that. Okay, so summation I also inside. So we see that the expectation value. Okay, so we should really write one more equation here. So this thing is also equal to trace A, and then this weird quantity of summation I, Pi psi psi. Okay, and sorry for another typo here. Okay. So this quantity, yeah, trace A summation I, Pi psi psi summation I here. Okay, and so what does all this done? All this done is we show that expectation value of A only depend on summation I, Pi, and this projected onto psi, this psi k psi bra. Okay, we see that expectation value only depend on this thing. Okay, and this is oh sorry, oh I have a typo here. Okay. Yeah, so this is what we call a density matrix. We see that the expectation value of any observable only depends on the observable itself, obviously, and this quantity summation I, Pi, psi, psi. Okay, and yeah, so we are going to see that this is our density matrix for every every probability state pair. Okay, and in particular, so let's we start with some terminology first. So we have a whole bunch of states associated with probability. Okay, whole bunch of states psi, each associated with probability Pi. Then we call this state of pairs Pi psi. We call it an ensemble. Okay, it's an ensemble of pure state. Okay, and in particular, so just some notation. So in physics, ensemble just means probability mixture of things. Okay, so the things here are the pure states. So this is an ensemble of pure states. Okay, and yeah, so here just terminology. So what we want to say is that we define this density operator rho I equal to summation I, Pi, psi, psi. So every example we can just write down this thing. This is in a matrix because remember psi is. So this psi is a column vector, psi is a row vector. So each of these psi is a projector onto psi, is a matrix, and we are summing over a whole bunch of projector is still a matrix. Okay. This thing is not a projector anymore, but it's a matrix. Okay. We are averaging over projectors. Okay. And yeah, so every example we can define this density operator or density matrix. And we are going to show that the density matrix totally describe our quantum system. Okay, so whatever things you can do on this example of PSI is actually determined only on this density matrix rho. And so let's skip ahead a little bit. In particular, this rho actually has a little less information than PSI because it's possible that different PSI give you the same density matrix, but so you can have a different pair of PSI and they can give you the same density matrix. And we think that the density matrix actually represent all the things you can know and do on the system. And so even though you might start with different PSI, we actually think you have the same quantum system. Okay. And we'll check, maybe not even enough time today, maybe next time, but we'll show you how this rho actually describe the evolution and the measurement of the system. And I guess you already see part of the reason why measurement just depend on this rho from this motivating derivation. So you show that if you want to, you will have any physical operator A, and you have any physical operator A, and you want to see its excitation value, then we have that. So the expectation value of A can be written with just this rho itself is equal to trace A rho. Trace rho A equal to trace A rho. But let's try trace A rho. Okay? Trace A rho. Okay? Just this derivation itself. And we only have 5 minutes, so let's do some writing here. So I just claim that there are some different PI psi pair that give you the same density matrix. Okay, so let's have some density matrix example. So maybe the example one is this 1/2 probability. So 1/2 probability you get a zero state, and 1/2 probability we get a one state. Okay, and, so it's this state. Okay, so then we can have a rho 1 equal to, now it's just write down things. So 1/2 and the projection on 0. So this is 1 0 ket 1 0 bra plus 1/2 and 0 1 ket times 0 1 bra and ket and bra. Okay, and so this thing is 1/2 and this is 1 0 0 0 and plus 1/2 0 0 0 1, and this is 1/2 times the identity matrix 1 0 0 1. Okay. Okay. And so this is example one. Okay. And so here is an example of how you calculate the density matrix from example. Okay. And now let's see something interesting. So we have example 2, that's something looks totally different from example 1, that is if we change the 0 1 basis to plus minus basis. Okay. Okay, so example 2 is still 1/2 probability. So 1/2 probability we have the plus state, and 1/2 probability we have the minus state. Okay. And so let's start with the Brandless calculation first. So let's just see how the maths work out. So rho 2 equal to 1/2, and we have 2 1 square root 2. Let's write down in slower way. 1 square root 2 1 1 times 1 square root 2. Excuse me. 1 square root 2 and also 1 1 plus 1/2 1 square root 2 1 minus 1 and 1 square root 2 1 minus 1. And let's skip the calculation a little bit, and so both of them has 1 square root 2 times 1 square root 2 equal to 1/2, then times 1/2 equal to 1/4. So everything is 1/4, and then the two matrices are is 1 1 1 1, just give you 1 1 1 1 plus this let's write this a little better. Okay. So this is 1 minus 1 times 1 minus 1. So this is 1 minus 1 minus 1 1. Okay. And so you see that it is 1/4 times the diagonal terms cancel, and diagonal term is 2 2. So this once again is 1/2 1 0 0 1. Okay. And so this might make you a little uneasy, because now if you think about kind of the physical interpretation of 0 1, it's kind of like you have remember that we say this 0 1 can be viewed as spin pointing either up down, right? So this is spin pointing 1/2 probability in the up direction, pointing 1/2 probability in the down direction. and this is spin pointing one half probability to the plus direction, 1/2 probability to the minus direction. So I think these are totally different things. This is spin pointing in either the z directions, these are spin pointing in x directions. But somehow in this ensemble interpretation or this density matrix formulation, we find out that if those two are classical mixture with 1/2 probability, and those two are classical mixture with 1/2 probability, then they are actually the same quantum state. They are both of the density matrix equal to this 1/2 1001. This is also 1/2 1001, and there is no way you can you can distinguish between this ensemble and this ensemble. Okay, and I think we are just on time, so let's stop here and see if there are any questions. Otherwise, we will continue on Thursday.